Questions about anything? Last time or anything? Well, today's a big day. I'm going to demonstrate the Fourier inversion formula for functions in the short space. But it's interesting that if you know them for functions in the short space, then you can get them. You can get the same thing for much more general functions, and in particular, the functions of moderate decay at infinity that we were looking at the other day, that Steins calls the M of R space. It works for them too. And those are pretty common in engineering and science problems because when you're dealing with finite energy, those functions do tend to decay at infinity fast enough to make all this stuff useful and make sense. Anyway, my main goal in doing this is so you sort of see the key ingredients and believe that they work, rather than nailing down every little detail. So we'll see how successful I am at that. So last time I showed you a key fact that if I take the function, kind of the Gaussian bump function, so e to the minus pi x squared, last time I showed you that phi hat is itself. To the Fourier transform of that phi is basically itself. It's e to the minus pi s squared. Same function, different name for the variable. So it would be reasonable to say that the Fourier transform of phi is itself. Okay. And I told you that I did this thing earlier in the semester, and I kind of did, but I want to do it a little bit more carefully today. So before I get rolling here today, I decided I'd demonstrate that lemma kind of again for you, so that to refresh your memory. And the lemma was that if f is a Schwartz function, then when I make a good kernel out of this phi, then phi sub epsilon convolved with f converges to f uniformly on the whole real line. Okay, so let's see. This is where we are making a bump function out of the classic bump function. That classic bump function has integral 1, and so I don't have to divide by a constant to make it have integral 1. And the classic method to turn it into a bump function is to take 1 over epsilon times phi of epsilon x. Okay. So the demonstration of this is, let's see if I take,
Is it epsilon x or x over epsilon?
you're right, sorry. That's x divided by epsilon. That concentrates the bump at 0. So, phi epsilon convolved with f at x minus f of x that stands for the integral of, it doesn't matter what order you do this in. So I can pick my favorite. And my favorite in this case, I'd write the other one and realize, oh, I don't like that. But my favorite, when I do it the right order, is phi epsilon of t, and I put the x minus t in the f part. I can put that x minus t in either spot I want, either in the phi part or the f part, because this thing's commutative. And that's a dt. And I look at that for a second and realize, oh, the integral of that bump is 1. So I can express f of x as something very similar looking. And that if I stick an f of x inside this integral, the integral of the bump function is 1, and I can pull the f of x out front and get f of x times 1. And that's the key to this thing. Then I realized that this can be written as an integral from minus infinity to infinity of a phi epsilon of t times f of x minus t minus f of x dt. And I claim that this goes to 0 uniformly as t goes to 0. So I claim this goes to 0, and in fact uniformly in x as t tends to 0. Okay, and let's see, why is that? This is a Schwartz function, so it goes to 0 to infinity really fast. So I can make it less than epsilon over 2. So let's see, here's the y. F of x, let's say f of t goes to 0 very rapidly as t goes to plus or minus infinity. So I can make both f of x minus t, I can make the both of those less than epsilon over 2. Let's see, it's going to be uniformly in x. So I can give me an epsilon bigger than 0. I can make it, let's see, f of x minus t dt. Yeah, I can make that less than f of x less than epsilon over 2 when x is big. So that would be x, absolute x greater than some b. And then I could use uniform continuity on the closed interval. Use uniform continuity of f on minus b to b to get a delta bigger than 0, so that f of x minus t minus f of x is less than epsilon when the absolute t is less than delta. And this is going to be true for all x. The ones that are far outside, the thing's already small, but and in the middle where I use uniform continuity, then yeah, that's where I need the uniform estimate. So it's kind of a sneaky way to ignore the big X. Anyway, once you have that, you let epsilon be bigger than 0. You get the delta as above. To make f of x minus t minus f of x less than epsilon. Let's make it less than epsilon over 2 when t is less than delta in absolute value. And then you take that integral and you get that phi sub epsilon convolved with f at x minus f of x. And you write that integral in terms of two pieces. The piece where delta, t goes from minus delta to plus delta. And that's where this thing is small. F of x minus t minus f of x. This is going to be the small one. So that's a good thing. And in the homework you did the last time, then we do have the integral where the modulus of t would be bigger than delta. Phi epsilon t times this thing dt. Okay, so I need to estimate these two things separately. Let's call this one I1 and this one I2. Okay, I'm using the good kernel properties here. So when I do I1, that function inside the integral, the f part, is less than or equal to epsilon. So let's see, I guess I should write it like this. This is less than or equal to, and here's one of the key properties of a good kernel. That kernel is positive. So when I take the absolute value under the integral sign here, I'm using the fact that this is a positive thing. So the absolute value doesn't go there. But the absolute value does go here. And that's less than epsilon. And so you do think, oh, that's less than epsilon. But from minus delta to delta, that's where the phi sub epsilon gets humongous. As epsilon goes to 0, so think, oh, darn, that's not bounded. But it has the key property that the integral of the whole stupid thing is 1. So the key property of a good kernel is that this is less than or equal to epsilon times the integral from minus delta to delta, where this thing is big. But this is an integral. It's not the soup. And the integral would be less than or equal to the integral of the whole thing. And the integral of that whole thing is 1. Here I'm using its positive also, so in fact, it's strictly less than this, because it's never 0. And this thing is 1. So I get epsilon. Oh, what did I want? This is less than epsilon over 2. I get epsilon over 2. Okay. And now we have to estimate, well, your homework. Let's see, I need to estimate integral 2. And there, the key is that since f is going to 0 at infinity, that thing, the f part, is going to be a bounded thing. So let's now mess around with I2. F, that's part of the Schwartz function thing, that f is bounded. f in an element of S implies f is bounded on the whole real line. Let's say that f of x is less than or equal to m for all x. Then when I estimate I2, I'd get that's less than or equal to the integral around gamma when t is bigger than delta of phi sub epsilon of t. And then when I take this here, I'd get m plus m. When I take the absolute value underneath the integral, I get two of those. I get, you look at it, I get the f of x minus t, I bound that by m, and I get the f of t, I bound that by m. So I get 2m when I do that. dt. And this is exactly something you bounded, and you showed this goes to 0 in homework. Oh, that was homework number 7. Homework 7 showed this goes to 0 as epsilon goes to 0. Once delta has been chosen and fixed for fixed delta. And we fixed it above. Okay, so we make that, oh, I've got 2 epsilons here, doggone it. So let's see, what should I have done? Let E be bigger than 0. I make this thing less than E over 2. I'll fix this. So this is an E over 2. And now I, for less than, what am I writing here? Yeah, so I should have written, this is less than E over 2. This is E over 2. And I get it less than E over 2, independent of the epsilon. Okay, so I haven't let epsilon go to 0 yet. So I can, because this goes to 0, now I can, this goes to 0 as epsilon goes to 0. So make it less than E over 2. And then you get the uniform limit. Okay, so those are the details. And we've worked on every little piece of it up to this point. And it works great. Okay, so let's see. We're almost ready to do the biggie here. There's one more lemma I need, which is a routine lemma. It's a beautiful lemma, and it's going to be important. If f and g are in the Schwartz space, then interestingly, I guess I'll write it like this. The inner product, I won't write it like that. I'll write it like this. Integral from minus infinity to infinity of f of x times g hat of x dx. This is kind of like those Parseval identities you figured out about series. And it's the same as f hat paired with g of x, like an inner product. That's not an inner product because there's no conjugate. in the second spot. And the proof is a routine thing. In fact, Stein didn't even want to do it. He relegated the proof to an appendix. It's basically just Fubini's theorem. So Fubini's theorem on, let's see, the function we're going to integrate 2 times is f of x times g of y times e to the minus I 2 pi x times y. Okay. And because f and g are in the Schwartz space, these integrals, the tail ends of these integrals are something we can ignore. So let's see, I'm going to integrate f of x, and then I'll integrate in y. Let's see, that when I'd have the function there, I'd have to have my g of y in here times e to the minus I 2 pi x y. Okay, I'm integrating dy here. And then I integrate dx. So that's an iterated integral of the function I wrote above. That's the integral on R2 of that function. So I guess I could write this as the integral on R2 of that function right there. That's the function. The area. I guess I should be more professional. I should call this h of xy. And then this would be the function on R2 of h of xy as an iterated integral. When you look at that in the middle there, this thing is this is the Fourier transform of g evaluated at x. So that's the first integral I want to see. But now when I do the Fubini's theorem, which I can do because these things die away at infinity so fast, Stein gives the details of why that's the case in his appendix. But it's kind of routine and not the main point that I want to dwell on here today. Okay, so let's see. When I change the order, first I'd integrate in the y variable, minus infinity to infinity. And when I change the order, I would get the g of y can come out now, since it's not involved in the other integral. And what's left is f of x times e to the minus I 2 pi xy dx. And the aha moment is that is the Fourier transform of f at y. So I get an integral of g of y times f hat of y dy. And that's when I realize, oh, that y is a dummy variable, change it back to an x. So we're done. Y is a dummy variable. I don't know why they call it that. Doesn't matter what you call it. Change it to x. Here in the second spot. So that's a pretty routine fact. Questions about that? Okay. So here's the drum roll. I'm going to demonstrate the Fourier inversion formula. And the amazing thing is, you only really have to check it at x equals 0. So it's kind of a shocking thing. Enough to check x equals 0. That's this big surprise. Let's see. So let's think, what does that say? The Fourier inversion would be saying f of 0 equals the integral from minus infinity to infinity of f hat of s times e to the minus I 2 pi 0 times s, which of course is 1. And so Fourier inversion is only the fact that f of 0 equals the integral of the Fourier transform. It's that easy. Okay, let's think about why that might be true. Let's see, I want to use that little lemma thing I just did. Hop. That's all I need. Okay, so let's think about this. It's kind of a trick. The trick integral from minus infinity to infinity of f of x times the bump function by phi sub epsilon of x dx. That's the convolution. So that's phi sub epsilon convolved with f at 0. And we know that goes to f of 0. As epsilon goes to 0. And now that looks kind of like my inner product. What happened? Sorry. So I'm thinking out loud here. That's going to go to f of 0, and I kind of want this to be g hat of something. G hat of something. But G hat of what? It's actually pretty easy to guess what the G should be. Because we have all these rules about the transform. So let's see. What do we know? We know phi of E x transform, the dilation is 1 over epsilon phi hat of s over epsilon. We have that formula. Okay? And remember, phi was its own Fourier transform. So that's the bump function. Let's see. Right, so the phi hat of E of epsilon, that's our bump function. That's phi sub epsilon of S. So what I get here is that I have that formula. I have the integral from minus infinity to infinity of f times a g hat and I know that integral, that's equal to the integral from f hat, I'll put it at s, g of s, ds. dummy variable. Which now, using this function g that I've chosen up here, this becomes integral from minus infinity to infinity f of x times my bump function. That's equal to the integral from minus infinity to infinity of f hat of s. And this thing is my phi of epsilon x. Epsilon s ds. And remember what that is. That's the integral from minus infinity to infinity of f hat of s. This is e to the minus pi epsilon squared s ds. And in the homework this last week, you showed that this tends to the integral. This was homework 8. Homework 8, this tends to the integral from minus infinity to infinity of f hat of s ds. As epsilon goes to 0. Because that thing becomes 1 on a bigger and bigger thing. Because e to the 0 is 1. So this is, sorry. As epsilon goes to 0. And on the other side, as epsilon goes to 0, this goes to f of 0. Because that's the bump function centered at the origin. That's it. So, we're done. We're done showing that the inversion formula holds at x equals 0. Questions about that? Okay, well, I claim that once you know it at x equals 0, you know it. So finally, I need to show that we're done for x equals 0. And now for the rest of it, to get it everywhere else, for all x, we use all we need to use is a little trick. The key is one of these formulas we had. The Fourier transform of the shifted function, f, I'll call it dot plus h. The translated function, remember that you write it out, change variables, and you get this formula. That's e to the ish f hat s ds. And so let's see if I was going to use this formula to do the thing. I'm going to let f of y equals little f of y plus x. What? Where's the integral? Yeah, that's not an integral. Why did I do that? Sorry. That's the formula about translating a function and taking its Fourier transform. So, if I use capital F of y as that translated thing, then f of x, that would be capital F y equals 0. And we know this formula for this thing. And so that would be the integral from minus infinity to infinity of f hat of s ds. But f hat, is the transform of that translated thing. And so that's equal to the integral from minus pi to pi of e to the 2 pi I sh f hat of s ds. And that's the Fourier inversion formula. So if you know it at 0, you just know it. That's the inverse Fourier transform. Okay, so that's kind of a last-minute trick. All the work was involved in the seeing it's true at the origin. So let's see, there's some funny facts to know. I'm not going to dwell on these facts because we're not going to use them, but they're in all the books. Facts is the Fourier transform takes S into S. And now we see that there's a Fourier inversion theorem, and the Fourier inversion formula looks just like the Fourier transform. And so, in fact, we just showed that Fourier inversion is very much the same thing. In fact, all you do is you realize all I'm doing is replacing the x by a minus x in the transform. We just showed F inverse is the same kind of operator. In fact, when you look at it, it's just changing an x to a minus x. That means that thing is actually 1-to-1 and onto. We conclude that F, Fourier transform, takes the short space to itself, 1-to-1 and onto. That's cool. So it's like an isomorphism kind of thing. But another big corollary, I guess that's just a fun fact, but a big corollary that we are going to use is the something called the Plancherel identity. And this is true for functions in the short space. For f in the short space, the L2 norm of f is equal to the L2 norm of the Fourier transform. That's the L2 norm on R. Namely, let's see, that would be the integral from minus infinity to infinity of f squared dx to the 1/2. And we can actually demonstrate this now. It's not hard. Let's see, what do I know? I know the integral from minus infinity to infinity of f of x times g of x, g hat of x, dx is equal to the same thing with the hats moved to the other function. Okay, so let's see. What if I want... I'm thinking out loud now. I want g hat of x to be equal to f of x conjugate. Then at least I'd get the one of those integrals on the left. And so if that's, I can make that happen. I can have that. If I undo the Fourier transform. So g of x is the inverse Fourier transform of f hat conjugate of x. Okay, let's see, what did that be? That would be the inverse, that would be, I better make that an x function. So I'd have the integral from minus, okay, I want the x to be, this would be 2 pi sx ds. And this would be f of x. What the heck am I doing? This would be f. I'm integrating with respect to s here, so I get an x to pop out. Okay. What am I trying to do here? I stare at that for a minute. Okay, so that's the Fourier inversion formula with f conjugate in this usual spot. And I've switched the variable to be a ds in the integral rather than the x, because I want the x to pop out on the left. Okay, I stared at that for a little while and realized, aha, that exponential thing is the conjugate of something. That is the conjugate of e to the minus I 2 pi sx ds. Conjugate. Right? Because that would be a cosine plus I sine. When I take the conjugate, it would be a minus I sine. And now I realize, aha, this is the, what is that? That's the integral from minus infinity to infinity f of s. This is the Fourier transform. I haven't done anything here. But now I'm taking my conjugate and putting it outside. So this is the Fourier transform of f at, oh, okay. Now I'm going to do, this is the Fourier transform of f at x conjugate. Okay, so when I look back and see what I get here, I start out with integral from minus infinity to infinity f of x, and here I wanted to get an f conjugate of x. And that would be the integral from minus infinity to infinity, and here I would get f hat of x, and the thing that goes here I just figured out is f hat of x conjugate. And so sure enough, that's the Plancherel identity. So the integral from minus infinity to infinity of the modulus of f squared dx now I just take the square roots. That's fascinating. That means that the Fourier transform is an isometry. It preserves the norm. And that's a fascinating thing, that is quite useful in the theory. The Fourier transform is an isometry. It preserves length in the L2 norm. On the short space, at least. But because of that, it means that you can take limits of Schwartz functions and get Fourier transforms of them. And L2, I'm going to discuss it next time, just from an informational point of view, because this is where L2 was. This is why L2 Lebesgue integrable functions were invented, because of this fact. You need to take limits of L2 functions in the L2 norm to be able to make the Fourier transform make sense properly. And so if you have a big, dense subset like the Schwartz functions, that's how you extend the Fourier transform to much more general functions. And so the moral of the story is that the right space to do Fourier transform is L2 of R in the Lebesgue integral sense with respect to Lebesgue measure. Because you need it to be complete. And it's not quite an undergraduate subject to study the Lebesgue integral and Hilbert space in L2, but next time I'm going to tell you about sort of what the words are and why it's going to be an important thing to do when you go to grad school in math, if you go to grad school in math. Any questions about anything? This is kind of the theoretical, what would I call it? The climax of the course that way. Things are going to get easier from now on, and I'm not going to dwell so much on technicalities. So next time I'm going to talk about Hilbert space. L2 is the quintessential Hilbert space. L2 and Fourier analysis. They really are linked in history. And even Fourier series have a lot to do with this concept of Hilbert space and L2. And of course, I'm not going to do any details, but I'm going to tell you the words and the facts. So it'll be one of those things where you can just sit back and listen. Hope. Last minute questions about anything? Yeah.
In the beginning of class of the convolution uniform convergence, that function that works for continuous and bounded functions, right? So why are we doing it for Schwartz functions?
Schwartz functions go to zero fast at infinity, so I get uniform convergence on the whole real line. That first time I did it, I only got pointwise convergence. Oh, I'd have to think about that. That's what I got hung up on the last time I did it. Because I have Schwartz functions now, I don't have to worry about the tail ends, because that part of they go to zero real fast out there, and so I just can ignore that part. Yeah. Okay, that's enough for today.